let's say we have the function f of x is equal to x to the third over 3 minus 2x squared plus 4x. And we want to graph this function, and we want to graph it accurately without using a graphing calculator or Desmos or any of that. And we want to do this with using calculus. So let's do that. So the few things we're going to define here, or we're going to need to graph this, is what happens to y as x goes to infinity. And this is not really calculus. I mean, you could think of it as limits, so I guess this is calculus. We can take the limit as x goes to infinity of this function, and we get y goes to infinity as well. Again, so let's do that really quickly actually. Limit as x goes to infinity of f of x. If we plug in large numbers here, x to the third is going to dominate over any of the other ones. So f of x, this will be infinity. So that's good to know. Now let's see what happens as x goes to negative infinity. Again, we can take the limit as f of x goes to negative infinity, and this is going to be the dominant term again, and it's going to be negative. So y is going to go to negative infinity. All right, so we know how the function reacts for infinities, so that's good. Now, let's also find, so in this case, we know there's no absolute maximum or minimum, right? Because it's going to go to infinity and negative infinity. But we can find some relative maximum minimums. So this is the first thing we found. We're going to find also relative maximum minimums, and then afterwards we're going to find inflection points and concavity, and we'll be able to graph it. So let's do our next thing, which is relative minimum and maximum. Well, we know that the relative minimum and maximum occurs when the derivative of the function is 0, right? So at some point, there's going to be some minimum or maximum, and that's when the function's derivative is 0. So let's take the derivative. So this is step 2, f prime of x, and set it equal to 0. So f prime of x is, well, 3x squared over 3, that's just x squared, minus 2x squared, derivative is 4x, so minus 4x, and then plus 4, and set this equal to 0. Let's figure out what the critical point here is. So we can factor x squared minus 4x plus 4 to figure out where x is 0. So sorry, where f prime of x is 0. So the factored version of this will be x minus 2 squared, because negative 2 times negative 2 is 4, negative 2 minus 2 is negative 4. And you could check this and make sure it works. So our critical point here is x equals 2. So at this point, the function either has a minimum or a maximum. And we don't know if it's a minimum or maximum yet, but we will figure that out pretty soon. Let's keep going. So this right here is a critical point. All right. Now the third thing we want to do is figure out the concavity of this function. So we'll do it right here. So we want to figure out where this function is concave up and where it's concave down. So first let's do concave up. We know this function is concave up, again, which means the rate of increase is increasing when the second derivative is greater than 0. So let's take the second derivative. Well, the second derivative is just the derivative of the first derivative. So we can use this equation here, take the second derivative, we get 2x minus 4. So let's figure out where this is greater than 0, which implies that it's concave up. All right, so let's solve. Well, this is a pretty simple equation to solve, right? We can add 4 on both sides, divide by 2, and we get x is greater than 2. So what I did is add 4 on both sides, and then I divide by 2. So for x is greater than 2, this graph is concave up. So we can write from 0, or sorry, not from 0, from 2 to infinity, we have concave up. And if you don't know what concave up means, I encourage you to watch the previous video. All right, now let's figure out where this graph is concave down. Well, it's concave down where the second derivative is less than 0. So we can say that f prime of x is f double prime of x is less than 0, which implies that 2x minus 4, which is the second derivative, is less than 0. And if we solve this for x, we get x is less than 2. So, right, so that makes sense because 2 is the inflection point, which concavity changes. So from negative infinity to 2, this graph will be concave down. All right. Now, let's see. Now, how do we figure out whether this point, which is 2, is a minimum or a maximum, right? A relative minimum or maximum. Well, we can think of what happens as we plug in a value that is slightly larger than 2. And we notice, so let's do that. So at x equals 2, we know that this is either a minimum or a maximum, right? So at x equals 3, if the value is greater than 3, that means this should be a relative minimum, right? And a value at 1, if it's also greater, then it should be this is a relative minimum. So let's see what happens. So at 2, if we plug in f of 2, we get 2 to the third is 8, so 8 over 3, minus 2 squared times 2 is 8, plus 8, that goes away, so we get 8 thirds. Now f of 3, let's see what that is. Well, f of 3 is 3 to the third is 27 over 3 is 9. 9 minus 2 times 9 is 18, plus 12, right? Again, all I'm doing is plugging into the function here. And let's see, let's sum this up. What do we get? Negative 18 plus 9, that's negative 9, plus 12, what is that, 3? Okay, so f of 3, let's see, is f of 3 greater than f of 2? 8 thirds is 2 point, it's less than 3, right? Because 9 thirds would be 3. So that means f of 2 is less than f of 3. And then if we check f of 1, we'll notice that it's also greater than f of 2. So therefore, f of 2 is a minimum. So relative minimum. And if that was a bit confusing, I encourage you to watch the relative minimum video, and that will help. So we know that that's a relative minimum. Okay, so I think we almost have enough information. Let's see if we're missing anything. We know that the function, as it goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to negative infinity. We know there's a relative minimum, x equals 2. And then we also know that the concavity is this right here. Okay, so let's go ahead and graph this. So the graph is going to be a bit small, kind of running out of space here, but we'll graph it right here. Graph it right here, and then we'll confirm on Desmos that our graph is right. So x, comma y. Again, I probably should graph this a little bit larger, but we don't have much space here. So first, let's graph as it goes to infinity. So as x goes to infinity, we go to infinity. And we also know that as x goes to negative infinity, we go to negative infinity. We also know that from negative infinity to 2 is concave down. So negative infinity to 2 is concave down. We also have to be careful because it's a relative minimum here. So we'll have to change something probably after we graph this. So concave down, this is 1, this is 2, relative minimum. So I'll draw something right there. That'll be the minimum. And then we'll go concave down, right? Concave down, concave down, concave down. And then from 2 to infinity, again, we have to be careful because it's a relative minimum. So we got to make sure any point near it is greater than 2, greater than the value at 2. And then from 2 to infinity, it's concave up. So it starts being concave up right here, like that. All right, let's see if we're missing anything. So this point should be this one, actually, right here. So at x equals 2, we have our minimum. So 2 is checked off. As x goes to infinity, our function goes to infinity. As x goes to negative infinity, our function goes to negative infinity. So that's checked off. From 2 to infinity, it's concave up. That's checked off. And from negative infinity to 2, it's concave down. That's checked off. So 3 is checked off. So our graph should look something like this. This weird graph here should look something like that. Now let's check Desmos and see if we got a good approximation. And it looks like indeed we did. At x equals 2, we have our relative minimum, which is right here. Our concavity is concave down from negative infinity to 2. And at 2 it changes, it turns concave up. X goes to infinity, y goes to infinity, x goes to negative infinity, y goes to negative infinity. So we are done.